Good day, class, and welcome back to my calculus class. So, right now we want to look at a very special concept in the study of calculus, and that is the concept of continuity. In this video, I will be looking at the three conditions for continuity at a point, and also describing the three kinds of discontinuities. In my next video, I will be covering continuity on an interval and the theorem for limits of composite functions, and also talking about intermediate value theorem. So let us start. Continuity at a point. Think about this function. You should know the behavior of this function at this point. Um, we have something like this for x squared. Now, the way to think about continuity is, let's say you are just moving on this function and you can go through the entire function without lifting your pen. Then you say this function is continuous. So we say many functions have the property that their graphs can be traced with a pencil without lifting the pencil from the page, just like I just did. Such functions are called continuous. At the very least, for a function to be continuous at a point A, let's say, for example, this is A. So for that function to be continuous at that point, at least that function must be defined at the point A. Does that make sense? That is, if we want to talk about continuity of this function f of x equals to x squared at point A, at least the function itself must be defined here. So that is the first condition. F of A is defined. That is, if I plug in that value A into this function, does it make sense? Is it defined? Is it meaningful? Okay, look at this figure. At this point A, we can see we can trace this graph. However, when we get here, there is a lifting of pen before we continue. So in that sense, we say f of A is not defined here. So because we lifted our pen when we got to that point. So the function f of x is not continuous at A because f of A is undefined. It is not here. Look at it. It is a hole, right? It is a hole. Okay. So looking at figure A, we said we must have the situation whereby this point is solid. That is, you cannot lift your pen. It is solid. So you can go through that point. You can trace it without lifting a pen. However, look at this point. Look at this graph. We do have that at point A, f of A is actually defined. It is there. Look at it. Solid. It is there. However, if we trace this graph as it is, if we trace it, sorry for, I need a straight line just like that graph. If I trace it, although it is defined here, but I still need to lift my pen to continue here. What that tells us is that it is not enough for that function to be defined at A. We need something more. So we say this function is discontinuous at point A. Why? Because the limit of that function at the point A does not exist. Now, you know the concept of limit. If you look at it from the left, it is this y value. If you look at the limit from the right, it is this y value. And they are not the same. They are not the same. Remember, for the limit of that function to exist, so I will say for the limit to exist, it must be that, let's say, we must have the following situation. We must have limit as x goes to a from the left of that function, and the limit as x goes to a from above of f of x must be the same. But in this case, they are not the same. The limits are not the same. So it then means that we need to put that condition as the second condition. That is, we must have that the limit of that function as x goes to that point must exist. And lastly, let us look at this figure. Now, the limit from the left actually exists, and it is this y function. No, that is not what I want. And it is this y function here. And the limit from the right also exists, and it is this y function. They are the same. So the limit exists. Furthermore, at this point A, the function actually is defined. You can say it is solid A. It is defined. However, it is not continuous because we still need to lift our pen here, meaning that there is another condition we need to look at, and that is, it is not enough for this function to be defined at A, or the limit to exist. It must be that the function's value is actually the value of that limit. So that leads us to the condition 3. So here we say this function is not continuous at point A because the limit is different from the value of that function at A. So we must add the third condition that this must happen. Putting all these conditions together, we arrive at the formal definition for a function to be continuous at a point. And this is the definition. A function f of x is continuous at a point A if and only if the following 3 conditions are satisfied. The first one, that function at point A is defined. Then the limit of that function as x goes to that point A exists. You know what that means? Limit from the left must be the same as limit from the right, and they must be equal to a real number. And the last condition is that that limit must actually be the value of that function at point A. If you can establish these conditions, then we say the function is continuous at point A. So this is very important, guys. A function is discontinuous at a point A if it fails to be continuous at A. That is just it. And it only needs to fail one. Once only one is missing here. Once we are missing one condition, then we say the function is discontinuous at point A. So how do we check if a function is continuous at a point? The first thing to check is check if the function is defined at that point. If f of A is undefined, then we don't even need to do anything. It means the function is not continuous at that point. So we need not to go any further. If f of a is undefined. So we can make our claim. No need to check others. That is enough to claim that it is not. But if f of a is defined, it is also not enough to say it is continuous, as we have seen earlier. It is not enough. However, it tells us that it is the time to move to step 2, compute the limit. And what that means is that you look at the limit from the left, look at the limit from the right. If they are the same, then we claim that the limit exists. If they are not the same, then we can stop, because we've seen that where f of a is defined, but the limit does not exist. So it cannot be continuous at that point. But if it is the case that the limit exists and it is a real number, then we move on to the last step, which is that value of f of a and the limits that we find, are they the same? If they are the same, then we say the function is continuous at a. If they are not, then it turns out that, well, f of a is defined, the limit exists, but since they are not the same, the function is still not continuous at a. But if we have f of a to be defined, the limit as x goes to a of f of x exists, and they are the same. That is, that's functional value at a and the limit as x goes to a of that function. If they are the same, then we conclude that the function is continuous at a. Let us take example to give this a better understanding in terms of concrete example. Using the definition, determine whether the function f of x equals to x squared minus 4 divided by x minus 2. We want to check if it is continuous at x equals to 2 at that point a, which is 2. And you need to justify your conclusion. Let us check. The first thing, step 1. Step 1, check if f of 2 is defined. So let us see. What does that mean? Can we plug in 2 into the function such that the function will make sense, such that we can get an output? It turns out that if we plug in 2 there, the denominator is going to be 0, which tells us that f of 2 is not defined. Since it results into the denominator being 0. Therefore, that is our conclusion. Therefore, what is it? F of x, that is the function itself now, is not continuous. It's not continuous. It's not continuous at x equals to 2. So you've given the reason. Since f of 2 is not defined, then our conclusion is that that function is not continuous at x equals to 2. Looking at the graph, let me show you the graph. We have seen this graph before in this class. So this is the graph of this function. And you can see at point x equals to 2, you can see there is a hole at that point. So, meaning f of 2 is not defined. And it is enough to show that, to prove that that function is not continuous at that point. Let us look at another example. In this case, we want to look at a piecewise function. Okay, the first step one. So one more thing I need to say there before I close this example is that since f of 2 is undefined, there is no reason to check for the limits. There is no point. One of the three conditions has failed. So we just stop. We can make our claim that the function is not continuous at x equals to 2. Okay, let us look at the example here. The first thing again is to check for f of 3. In this case, it is 3 at x equals to 3. Now, let's see this function. We need our input to be 3. Remember, this is a piecewise function. You need to look for where x is 3. X is 3 on this domain. So that means we are using these parts of the function. F of 3 is defined because f of 3 equals to, so we are going to use these parts, minus 3 raised to power 2 plus 4, which is negative 9 plus 4, which is negative 5. So we can see f of 3 is defined. So it is defined, that function is defined at that point. However, it is not enough for us to make the claim that the function is continuous at x equals to 3. So we need to go to the next step. So let us go to step 2. Step 2. And what is that? We need to check now for the limit, if the limit exists. So we check for, or we compute the limit, for the limit. To do this, we need to find, that is, we find limits from the left, that is, as x goes to 3 from the left of f of x. We need to find the limits as x goes to 3 from the right of f of x. I hope that makes sense. So let us find the limit of f of x as x goes to 3 from the left. You go back to the domain. Here we have, let me clear this. Now, here we have values of x less than 3. If you have this is 3. Anything less than 3, that will be from the left. Anything more than 3, that will be from the right. So it turns out that this function will be used from the left. So we have minus, be careful, because this minus is outside. So outside, then our x is 3 squared plus 4. Again, that is negative 5. Now let us see from the right now. So from the right, look at the domain. Any value that is more than 3, use this function. So that is 4 times 3 minus 8, which gives us 12 minus 8, which is 4. We can observe that, let's say we observe that the limits from the left is not equal is not equal to the limit from the right. So, therefore, you know what our conclusion means there? Therefore, limit, what that tells us is that limit as x goes to 3 of f of x does not exist. Because if it exists, this number, this real number, and this real number must be the same thing. And since they are different, it means the limit of that function as x goes to 3 does not exist. Now, we see this condition is fulfilled. However, this condition is failed. We do not need to go to step 3. Here we just conclude. Conclusion. Conclusion. F of x is not continuous. It's not continuous. It's not continuous at x equals to 3. Since limit as x goes to 3 of f of x does not exist. So look at the way I showed everything, very clear. So when you write, make efforts to write it out clearly so that someone who is reading your work will understand what you are communicating to them. Okay, and this is the graph of that function. So you see, the function is not continuous at 3 because the limit does not exist. If you look at from the left, the limit is trying to get to the y value here. However, from the right, the limit is trying to get to y value, which is here. So they are not the same. Okay. Let us move on. Another example. Using the definition, you know what we mean by definition? That is our 3 conditions. Determine whether the function is continuous where at x equals to 0. Remember, step 1 from the definition. Step 1, check. We need to check f of 0. Or let's say check if f of 0 is defined. Again, this is a piecewise function. This is where x is 0 and it is 1. It is a constant function there, so it is defined. We observe that f of 0 equals to 1. Hence, f of 0 is defined. Now with this, that is a good result, but not enough. So we need to move on to step 2, which is to compute the limit. Compute the limit as x goes to 0 of f of x. And to do this, we need to find, that is, find the first one, limit as x goes to 0 of f of x. From the, let's say from the left, I write this. So let us do from the left. Okay. Limit as x goes to 0 from the left of what? Our function, f of x. Let us return to our function. Where do we have our function? Where do we have x going to 0 from the left? Where? Here we have, this is only happening when x is 0. When x is not 0, it is this function. That is, either it is negative or positive, it is this function. This one is just for when x is 0. Every other thing, you consider this part. Now, it turns out that we will have limits as x goes to 0 of sine of x divided by x. Remember, we have solved this in my last class, in the earlier video, that this result is 1. So you see, this is why you must know this special limit of n. You must be able to retrieve them anytime you need it. That is not enough. You also need to find limit as x goes to 0 from above of that function, which is limit as x goes to 0 from above. Again, from my explanation, I will use this part again because that is where x is not 0. That is, either it is negative or positive. That is the part I'm going to consider. So sine of x divided by x. And again, it is 1. Oh, look at that. They are the same. This implies that the limit as x goes to 0 of f of x is 1. We can make that clear. Okay. Now, condition number 1 is satisfied. Condition number 2 is satisfied. It means we need to go to step 3. It is not enough for the first 2 conditions to hold. We need to check in for 3. And the last one is check if the limit as x goes to 0, that point of your function, if it is the same as when you evaluate that function at that point, 0. Put differently, check if your answer in step 1 is the same as your answer in step 2. We observe that limit as x goes to 0 of f of x equals to 1, and it is the same as f evaluated at 0, right? Remember, here, it is 1. And this guy is 1. They're the same. So we can claim that, therefore, f of x, that is that function now, is continuous. But not just like that, it's continuous. Where is it continuous? Remember, we only check it for that point. So we say f of x is continuous at x equals to 0. So, well written. Okay, now you should pause this video and go ahead to solve this problem. Using the definition, determine whether the function is continuous at x equals to 1. So just go through the same idea we have used and solve this problem. Please, I want you to be able to write it diligently, just as I did. This is a good way to communicate your work to someone reading it. Okay. Next, we want to consider some theorem. Continuity of polynomials and rational functions. Remember, we have done something on polynomials and rational functions in previous lessons. We talked about the limit polynomial functions and the limit of rational functions, that their limit exists if at that point, the point we are considering is in the domain, right? So our claim here is that polynomials and rational functions are continuous at every point in their domains. At every point in their domains. Yeah, I would just say recall that limits as x goes to a of, let's say, p of x is the same thing as p of a. Do you remember this theorem where we actually proved this, that, let me say, where p of x is a polynomial. It's a polynomial. It's a polynomial function, right? So we proved this earlier that this is the case. And now look at what we have here. That is the same thing. That is the same way we define continuity. The limit exists on the left-hand side. That is the claim that the limit exists. And on the right-hand side, we are saying that limit is exactly the value of that polynomial at the point A. So that is the proof. That is the proof. Also, we have also shown, we have shown that the limit as x goes to a of p of x divided by q of x equals to p of a divided by q of a for q of a not equal to 0. We have also, this part is a direct consequence of our work here. I believe that is in lesson 3. So that is just to show you that polynomials and rational functions are continuous at every point in their domain. If that point is in the domain, then it will be continuous there. That is all what we are saying. For example, for what values of x, is f of x equals to x plus 1 divided by x minus 1 continuous? Well, since f of x is a rational function, which is continuous at every point in their domain. We observe that f of x is not, okay, our question is for what values of x is f of x continuous? Okay, we observe that f of x is continuous for all x except when x equals to 5, since f of 5 is undefined. So that is the direct application of what we proved here. If it is a polynomial function, it will be continuous at every point of x that is in the domain. And remember, for a polynomial function, it is the domain is from negative infinity to positive infinity. So maybe that tells you something. And for rational function, that is when you have a polynomial on another polynomial, then we need to be careful so that the bottom will not be 0. And in that sense, we say that rational functions are continuous for at every point in their domain. For this problem, 5 is not in the domain of that function. So that is why we remove it. And we say this function is continuous at every other point, but when x is. So I will also leave you with this. Pause this video and do try it too. For what values of x is f of x equals to 3x raised to power 4 minus 4x raised to power 2 continuous. That should be pretty easy for you. Now let us look at types of discontinuities. We have discussed continuity, and we have talked about when functions are not continuous. So let us talk about the types of discontinuities that we have. The first one we talk about is removable discontinuity. Removable discontinuity is when you have the limits. The limit actually exists. You have the limit. It exists. But the value of that function at A is not the same as that limit. Then we say it is a removable discontinuity because the limit is actually the same. That is, the limit from the left is the same as limit from the right. But we still have that it is not continuous at that point. It means it has been removed. So removable discontinuity. Now, a situation whereby the limit from the left is not the same as limit from the right. So we say there is a jump. So there is a jump. So we call it jump discontinuity. So we say there is a jump. It's a jump discontinuity. And when we have a situation whereby as you approach that point A, what is happening is you're having vertical asymptotes. Then you say it is infinite discontinuity. More formally, we say f has a removable discontinuity at A if the limit exists. F has a removable discontinuity at A if the limit exists. But what happened? Note, when we say that the limit exists, we mean that we are having true value, a real number. But the problem now is that the limit exists, but the value of f of that A is not the same as that L. I say it's not L. So we say it has been removed. Now, f has a jump discontinuity at A if the limit from the left and limit from the right both exist, as in this case, you can see the limit from the left exists, the limit from the right exists, but they are not the same. Okay, they are not the same. So in that case, we say there is a jump discontinuity. You just need to be able to visually understand it. And that is why I'll always give you the picture first. So just look at it. The limit from the left is not the same as limit from the right. So there will be a jump, right? When the limit is actually the same thing, but the value of that function is not what the limit is going to, then we say that point has been removed. So removable discontinuity. When the limits are not the same, there is a jump. Okay. Um, then we say f has an infinite discontinuity at a if the limit from the left or the limit from the right is having positive or negative infinity, just like we have it here. You are looking at the limit from the left, it is either tending to positive infinity or negative infinity, or you look at it from the right and it is either tending to positive or negative infinity, then we say we have infinite discontinuity. And you only need one of them to happen. Okay, moving on, let us consider example. Classify the type of discontinuity we have in example 1. Let us return to example number 1. I remember we had that, okay, x squared minus 4 divided by x minus 2 at x equals to 2. Okay. That is f of x equals to x raised to power 2 minus 4 divided by x minus 2. The question is, what kind of discontinuity do we have here? We know that f of 2 is undefined. We've already defined that. F of 2 is undefined, which makes the function discontinuous at x equals to 2. We already know that. Now, remember what we know now is that function is discontinuous at x equals to 2. But we don't know what happened, why it is. Okay, we know why. I take that back. We know that f of 2 is not defined. That is, it is not there. But we need to know more to be able to classify this. So to do that, we need to actually check for the limits. So next, we need to compute the limits. Compute the limit as x goes to 2 of x squared minus 4 divided by x minus 2. We have actually found this one in our previous work. So this is limits as x goes to 2. You remember how we solved this? We use difference of 2 squared, or we factor this, so plus 2 divided by x minus 2, where x is not equal to 2. And this is, in this case, we can say this guy takes care of this guy, and we have limits as x goes to 2 of x plus 2, which is equal to 4. Now, look at that. The limit exists. Are you getting that? The limit actually exists, but we have the situation that the limit exists, that is, limit from the left, limit from the right, they are the same. But at that point, x equals to 2, it is not the same as what we are getting for the limit. It means that point has been removed. So we can conclude. Conclusion. we have we have a removable discontinuity, discontinuity at x equals to 2. Okay. Um, Classify the type of discontinuity we have in example 2 as removable, jump, or infinite. Again, let us look at the function we have in example 2. Okay, example 2 is we just take this. Example 2 is a piecewise function. So let us, okay. We know, because we've already done that, we know that f of x is discontinuous, discontinuous at x equals to uh, 3. How? Because because the limits, let us revisit that. It's about the limit, I believe. Where is it? Okay. So because, yeah, can you see? The limit from the left is not the same as limit from the right. So we'll say because the limit as x goes to 3 of f of x does not exist. Now, this function is discontinuous at x equals to 3. Why? Because the limit does not exist. And from our calculation, we realize that that limit does not exist because limit from the left is not the same as limit from the right. So you will see there is a jump. Therefore, I will say some things before I conclude, because it is, we need to be careful. So let us say does not exist since, let me write more, since limits as x goes to 3 from the left is not the same as limits as x goes to the right, as x goes to 3 from the right of f of x, then we have a jump discontinuity. Discontinuity at x equals to 3. So let us do some recap. When we have this, our claim is that the function is discontinuous at x equals to 3 because f of 2 is undefined. However, we don't know, that is not enough to be able to classify that. Let me show you why. Look at this graph here. F of A actually exists, and it is this. F of A exists. So it is not enough for us to know the type of discontinuity we have here. Also here, f of A actually exists here. It is here. So it is not enough if it is defined at that point. So we really need to talk about the limit itself. So that is why you see that we are still talking about the limit in both situations. Okay. I hope that makes sense. Okay, this is another example. Determine whether, so this is a brand new problem that we have not seen. Determine whether f of x equals to x plus 2 divided by x plus 1 is continuous at minus 1. If the function is discontinuous at -1, classify it as removable, jump, or infinite. So in this case, we need to start from the beginning. Okay, f of x equals to x plus 2 divided by x plus 1. Remember, we need to check for continuity first. Okay, so we observe at this point we should be matured now to see some things without much work. We observe that f of x is undefined at x equals to -1. How do I know? If I plug in -1 here, my denominator will be 0. So it doesn't make sense. So the function is undefined at x equals to -1. And that is enough to disqualify that function to be continuous at x equals to -1. Conclusion, f of x is discontinuous or not continuous. It's discontinuous at x equals to -1. The next thing now is to classify that discontinuity, if it is removable, jump, or infinite. And to do that, we need to talk about the limit. So let us see the limit from the left as x goes to -1 from the left of f of x. So x plus 2, oh, sorry. You will see that in this case, so that is limit as x goes to -1 from the left of x plus 2 divided by x plus 1. This is a situation whereby we are having k over 0, this form. This is a situation whereby we are having that. And if you remember how we solved this, that is in lesson 3. We solved this by saying we need to, bring apart, we need to separate that part that is making the denominator to be 0. So to do that, we have, this is limit as x goes to -1 from the left of, so I can say this is x plus 2 times 1 over x plus 1. I can write it that way. I hope you remember that part. If not, please revisit lesson 3. Equals to, now, in this case, I can write it using law of limits for products as x goes to -1 from the left, x plus 2 times limits as x goes to -1 from the left of 1 over x plus 1. So let us take the limits. Since this is a polynomial, this part is a polynomial, if we throw in that value, we have -1 plus 2 times. Now, this part that is making the denominator to be 0, we are not actually going to substitute there. We are going to visually think about it or mentally think about it. Now, look at this 1 over x plus 1. Imagine plugging negative number, see, -1, then you are coming from the left. So imagine putting negative number here and you are dividing 1 by that number very, very close to -1. So what do you think will be happening? You are dividing by a number that is very close to -1, right? So what will be happening to this entire guy here? Say, for example, you are picking -1.1. So, or -1.001, -1.0001, and so on. And you're adding 1, adding 1, adding 1. So you would see that you are getting something of this nature, -infinity. We have done something like this in our previous lessons. And in that case, it turns out that we have 1 times something like this, which is a -infinity. So, in fact, that is enough. We don't even need to do any other thing again. We do not need to do anything again because we have already fulfilled one part that it is leading us to infinity. From this, we can conclude. Therefore, we have an infinite discontinuity at x equals to -1. That it is enough. You can still go ahead to see from the right. So for the sake of knowledge, let us just to help you remember how to do the form k/0. So I will, okay. So let me just say, this is just, I would say not necessary. Okay, but just to remind you of some things. So limit as x goes to -1 from above of f of x equals to limit as x goes to -1 from above of what is x plus 2 over x plus 1. X plus 2 over x plus 1. Again, I will do the same thing. I will separate that limit as x goes to -1 from above. So x plus 2 and limit as x goes to -1 from above 1 over x plus 1. And if I'm plugging in -1 here, this part will be 1. And this part now, I'm coming to -1 from above. From above. So which means any value I'm picking for this will be less than 1, and it will make the whole of this guy here to be positive. However, a very small number. I'm dividing 1 by a very small number, so which means this part is going to be positive infinity, and everything is positive infinity, right? We can claim that the limit does not exist. Well, yes, because this is -infinity, positive infinity. But it is enough for us to know that there is an infinite discontinuity at x equals to -1, even by just getting this one. So I hope that is clear to you. So go ahead and pause this video and solve this. So I'm making 3 try it in this video. And yes, I'm going to be ending this video at this point. I hope you enjoyed this video. So keep learning maths, and I will see you in my next class. Bye for now.